So lecture 3. Now we get to move into some new things where we're going to use as the basic ideas what we've covered in the last 2 sections about time stepping for solving differential equations. And what we're going to do on Monday, I should point out, is that when Monday comes around, I'm going to bring my laptop in. We're going to do programming in class. So one of the things that it's kind of half lecture, half programming. We're going to build little codes in class that will be very closely related to homework 1, which will be posted by this afternoon. Promise. I'll do my left hand instead because you can't hold me to it. No, it'll be up there. I promise, sort of. I'm just a little behind, but the first homework will be up. It's very closely related to what we're going to talk in the last half of this lecture, actually. So I'm laying the groundwork to set you up for starting to think about this homework problem. So what we're going to consider today are boundary value problems. Boundary value problems are a little bit different than what we've done so far. Typically, what boundary value problems are is a differential equation that instead of imposing that at time something, time t equals 0, for instance, I start my system off and watch it evolve in time. Instead, boundary value problems are something where you have some kind of dynamics or effect where the boundaries are actually pinned, for instance, or the boundaries have some kind of constraints on them. A good example of this would be what you did in maybe statics mechanics, where you have an elastic rod pinned at the ends and you put a load on it. And you say, okay, there's some differential equations which governs how this beam would bend. And so, but now instead of watching this thing bend in time, you're hoping it's not bending in time. You just hope that you put the load on and it stays in a certain position. How do you calculate that, given the equations that govern this thing? So the typical way to think about a boundary value problem, we'll do second-order boundary value problems. But you can generalize this to the ideas here, higher up, is we want to consider some quantity y, where instead of specifying that time t equals 0, I know the state of the system, what you specify is that at one, and this is going to be now specified just on some interval, a to b. So t here is, we've typically referred to it as time, but now t is sort of like a spatial extent. Okay? It's like x instead of t. I could have used x. But it's a dummy variable, so who cares? And what you find is that for a general boundary condition, you would have something like this. At one boundary, you specify a relationship between the function and its derivative. At the other boundary, you specify another relationship between boundary and derivative. So this is the formulation of the complete problem. You have some equation up here that is a differential equation, but now you have the constraints at the 2 endpoints. So for instance, maybe this thing, you know, over here at A and at B, you have what y looks like is maybe something like this. Maybe that's what your solution looks like. Maybe that's your rod that got bent, and that's its state. Okay? You'd be worried if that was an airplane. But it's not an airplane. It's like a toy, maybe, and then that's what it's supposed to do. Okay. So these are your constraints, and then you want to understand what actually leads to this shape formation in there, given the equations of motion, or given the governing equations for this thing. So the question we can ask is, well, how do you solve this now? It's very different in nature than what we did before. What we did before is we said, okay, let's just take this thing for a time-dependent problem that we were working on, and we said, discretize it. Like we said, okay, we have a slope formula, and we said, okay, now my solution now, I just basically built the iteration scheme. Solution now plus a little bit gives me the solution in the future, and then you just put this in an iterative loop. This is how you step it up. And you step it up because you give the solution at time 0. But look at the difference here. What you're saying is, I start off here at some time, and instead of specifying my complete state of the system. I specify here, and I have to specify it in such a way that in the future I hit this point. Okay, so if you think of it as a time-dependent problem, what we've typically done, we specify everything here and just let it evolve, go forward in the future. But now I have to let it go forward in the future to this B, and I have to be very specific about what I'm trying to hit in the future. Okay? Now how do we do that? How do we take what we've done previously and incorporate it into this kind of idea? Let's start off with something a little simpler, which is we'll go back to this second-ordered equation, generally nonlinear. We're going to simplify the boundary conditions for a moment, just to sort of help illustrate what we want to do. At A, it's alpha. At B, it's beta. Those are my boundary conditions. And I just say, I have to start here, I have to hit there. How do I make that happen? Okay, well, here's one thing we can do. This is a second-order differential equation. For second-order differential equations, if you're solving them in time, because it's second order, it requires two initial conditions. You can think of a second-order differential equation, if you go back to your typical theory of differential equations, whatever the order of the equation determines the number of initial conditions you have to specify to uniquely determine the solution. Notice that with this here, I'm only specifying one initial condition over here. For second order, I have to specify two. The other one is specified over here, but what I can do is I can do a sleight of hand on the problem, and I say, why don't I do the following? I'm going to do what's called a shooting method. And the idea here is to say, I know that that has to be satisfied at A. I also have to specify one more thing if I want to think of it as a time-dependent problem. And so I will specify also this. I will specify that the derivative is big A. What's big A? Well, I don't know. I can make it up to be whatever I want. Now, here's the deal. What you're going to do is you're going to write an iteration scheme which basically fools around with this A. Because there's one freedom. You can pick A to be anything. I'm going to try to pick A just right so that when I start from this initial condition, I end up right there satisfying that like I'm supposed to. Okay? I don't know what this A is before I start the problem. And so you can start thinking about how do I develop then a computational algorithm so that I can get the solution. This is what the shooting method does. So here's the structure, the algorithm for this thing. Okay? And let's talk about what we want to do here. I can pick some A values here. And let's talk about what they do. So let's suppose I pick a value of A1. I start here with a slope of A1. Remember, this is giving me the initial slope I'm launching with, essentially. This is what's called the shooting method. I'm going to start here, and there's a certain slope I have to get it exactly to hit this. But I'm picking some generic A. Suppose I pick some A1 that took off along that direction. Well, maybe it takes off here and it lands there. That's not where it's supposed to be. It's supposed to be up there. So I've undershot. Suppose I pick another value, A2, a slope too high. Well, maybe it goes up like this and ends up here. That's also where it's not supposed to be. But the thing I notice is, if I were to pick an angle somewhere between A1 and A2, I might have a chance of getting closer. Okay? This, in some sense, should make at least qualitative sense, because the reason it's called a shooting method, because it's very much like what you would do if you had a mortar rocket and you were trying to hit a tank over here. You would launch a shell. If it went too far, what would you do? You'd adjust the angle. And if it went too like that, you'd try to adjust the angle again. Somehow, you know, if this angle went too slow, went too low, this one went too high, you know it's in between there, and then eventually you go in and okay? And since we are actually in a war and all that, maybe I should just defer from making more references. Like I said. Okay, but that's the idea. It's the shooting method. This is why it was called this. It's really, it makes a lot of sense from the perspective of launching projectiles. When you have this thing, all you have to do is adjust the angle of your launch to try to hit a target. And this is exactly what we're doing here. This is the angle of your launch for the differential equation. I adjust it, and what I want to do is find a systematic way of adjusting it so that I can get the solution I need. So the algorithm is going to be the following. First, solve the differential equation just with the methods we learned from the last two lectures. Time step, pick your initial conditions, let it evolve in time, with these initial conditions. Easy enough. The second step of the algorithm. You basically solve this all the way to t equals b. In other words, solve this thing up all the way to get to the end of your interval. Now, when you're at the end of the interval, what you want to do, you want to figure out what's your value of y of b. Okay? And you want to compare it with beta, because that's what it's supposed to be. When you just solve it with some a, you get some value of this. Is it beta or not? If it's not beta, you've got to adjust your a value. Okay? Adjust a. So I'm going to put plus or minus, meaning make it go more or less, depending upon if you overshot, undershot. You have to know something about your problem to know whether a higher a value makes it go up or down. Okay? And we'll talk about this on Monday when we actually come in and program and start doing some programming on some boundary value problems. So I want you to adjust a. That's going to give you a new launch angle. And then finally, so this is the basic algorithm. You just loop this. Keep adjusting a, keep adjusting a, keep adjusting a, keep adjusting a. You need one if statement in there saying, look, if you hit it, stop. Or really what you need to say, if I get within a certain tolerance. Okay? Not to beat this example to death, but there's a tank. Pretty much if I get within 5 feet of the middle of the tank, it's still on the tank. It's going to blow it up. You have to just know what tolerance you want here. How close do I need to be to this? Is 10 to the minus 2 okay with you? Is 10 to the minus 6? Depending upon the application you have in mind, that typically determines the tolerance level you've got to have. Okay? So what you have to do is decide, specify your tolerance. This is your whole algorithm for this thing. So you solve it with some launch conditions and some initial thing with some angle. You find out what is the value it actually, what is it supposed to be. Adjust your a. See if you've actually hit the target in the first place or that you're within a specified tolerance. If you're not, come back again, do it again until you hit the specified tolerance. End problem. Okay? Fairly simple, really. And how would you do something like this? Do something like this. In this problem here, you can think of it as I've launched A1 and A2. A1 I was too low. A2 I was too high. So you say, okay, I know it's between there. One of the easiest things to do is what's called a bisection method, which is say, okay, how do I pick my new angle? So when I've done this, I can say, okay, how about if I pick a new angle, A3, was halfway between A1 and A2. You know, just cut that angle in half. Okay, so that's somewhere halfway between, and then maybe I launch it, and maybe it ends up there. That's my A3. Still not right. But now, notice. Oh, am I dead? Okay.
No, it's pop. Well, we'll have to get to the blue.
All right. Okay. All right, we're all on? Okay. I'm good? All right. All right. Okay. So that's what A3 does. Now notice I've gotten closer. Now I know it's between A3 and A2. So my next angle I want to pick maybe is A4, which is halfway between A3 and A2. Now I launch somewhere here. Maybe I do this. Now I know it's between A4 and A3. You see, you keep cutting it in half, until you finally get to within the tolerance you need there. Okay? And you want an algorithm that's going to do this for you. So notice already, within your structure of programming, you have a loop to cut angles. So that's an iteration procedure. You're going to say, okay, a for loop that's going to be in there that's going to keep cutting angles. Keep cutting, keep cutting, keep cutting. Now within that for loop, there is a solution. Every time you cut this angle, you've got to solve this equation. So there's an ODE to solve. Well, that ODE has an iteration in it, right? I mean, this is the whole point of what we did in the first 2 days, which is all these solution procedures for differential equations are just simply iterations. Now within that iteration, after you get done with it, you have basically if statements. You have two sets of if statements. The first if statement is you say, okay, if I'm above or below the target, I've got to figure out what's the next adjustment to my angle. You do make that adjustment. That's your first if. Your second if I've hit the target, stop. Okay? So you see, that's how the algorithm is going to be for something like this. A for loop with the ODE solve, which is an iteration scheme, two if statements. That's your whole code. All right? So it's important to start thinking about, when you think about writing a code, think about it from an algorithmic point of view, because that's all we're going to be doing in this class, is how do you do this? Count up how many for loops you need and if statements you need. Build them. Okay. Any questions on that so far? So that, then, is the basics, the basic idea of what we want to try to consider. Now, I'm going to illustrate how to do some of this, or the setup of this, in an example.
Are there methods to solve boundary value problems? Because you explained that as the shooting method, right?
Yeah.
Is that a
Yeah, so, okay, so, good question. So what I've talked about here is the shooting method. There are other methods, and I will introduce another method, which is a direct solve method. We will also do that, and you also do that for your homework. And that will be, I believe, Wednesday's lecture next week. So always keep in mind that for any method, there's usually at least more than one couple methods that have been developed over time that are appropriate for these type of problems. And often is the case that one method is better than another for some specified reason for a given problem. Okay? So this method is very nice, for instance, when we start thinking about if you start doing a nonlinear problem. So if you come back to here, this is generically a nonlinear problem. When you have a nonlinear problem, the shooting method is quite nice, because solving this nonlinear problem is no big deal for the time-stepping routines we've developed. He doesn't care about the nonlinearity. The direct solve method, what it does a Taylor expansion of everything, and what you end up getting out of it is AX equal to B, a big linear system of equations. That's if it's linear. If it's nonlinear, you get a nonlinear system of equations. Typically, you don't want to solve nonlinear systems of equations if you can avoid it. There's no guarantee that you'll get an answer. There's no guarantee there is an answer. All these kind of issues come to haunt you. Ooh. Okay. All right. But we will consider the other methods. Okay. So let me erase, and we will start specifically on an example that is directly related to the first homework. So really setting up the groundwork for what we want to start to understand for doing the first homework. A lot of what I'll lecture about in class will be directly related to the homework. So, and there's a lot of code we'll write in class that's going to be directly related to the homework, so just keep that in mind. The notes also, if you've seen them, especially like, for instance, next lecture has a bunch of MATLAB code in it. So that code can be directly, you put it right in, write your own code directly out of that to do these examples. Okay, we're going to try a different pen. All right, here's what we want to consider. This problem, let me write it down first. With my boundary conditions and with n of x given by the following. There's a whole statement of the problem. Now what this essentially is, and we will go through this in the homework, this is the equation that governs how you get the electromagnetic propagating modes in an optical fiber or a waveguide from E&M theory. Or it's also the Schrodinger equation, the typical one you think of for quantum mechanics, of trapping a particle in a potential. So it's quite, makes its rounds in different fields of application. And the big deal here, we want to solve this thing. We want to actually find out what are the psi of n and associated beta of n that actually solve this problem. Turns out this is an eigenvalue problem where beta of n is your eigenvalue and psi of n is your eigenfunction. Okay? Now, n of x here is going to be very important for us. N of x is given by this functional form here. And if you plot n of x normalized by n naught, what you get is at 0, -1, 1. It looks like a little parabola like this, with the value of 1, and then it's 0 elsewhere. And this is important in E&M. This is your index of refraction, higher index of refraction that you have inside the waveguide itself, which traps the electromagnetic energy through total internal reflection. In quantum mechanics, this is a potential well from an atom or something that would trap these probability states, densities of trapping electrons, essentially. Okay. So, if you've taken those courses and you know a little bit sketchy about them, great. If you haven't, who cares? So all the comments I made, or you can just erase them from your mind, but it doesn't matter so much for what we want to do. A couple things I want to point out about the problem. First, look at these boundary conditions. All I'm requiring is that the solution goes to 0 at plus and minus infinity. That's fine on an analytic level, but remember about computing, infinity can't be handled by the computer very well. Okay? Neither can infinitesimal quantities. Okay? So if you actually solve this problem, you're not going to solve it on a domain which goes from negative infinity to infinity. You're going to solve it on a domain which goes from like negative L to L, where L might be big, but it's finite. Okay? So that's the thing. And what we want to do is find solutions to this. And we want to find these solutions, and we want to what's called normalize them. So we want to find the solution psi of n and beta of n that satisfy this problem such that they're normalized. In other words, I take the absolute value squared of these solutions, and I set them to 1. Okay. Facts for the boundaries. First of all, when I solve on a computational domain, notice that x goes to plus and minus infinity. But on the computer, my x is only going to go to plus and minus L, where L can be a lot bigger than 1, but it's a finite domain. The computer doesn't handle infinite domains. You can't. Okay, that's first observation. Second observation. What are the boundary conditions we impose? Notice this thing says that the solutions are going to 0 as you go to infinity. They're not 0. This is an important fact. These boundary conditions don't say the solution is 0. They always are just going to 0. What does that mean? Let's try to make sense of it. So let's go back to the equation. And this is what the n of x looks like here in this equation. Notice, if we take the range x, absolute value of x is bigger than 1. In other words, we're outside of this little region here. This is 0. Bless you. Right? So what ends up happening with this equation, that's 0. And we can look at what's left. And that's exactly what we're going to do. We're going to say, okay, for absolute value bigger than 1, our equation then just simply becomes second order differential equation, constant coefficient. I know how to solve these pretty easily. Okay? In particular, you can solve this, and it has the generic solution of the form. It's a second order differential equation, has two linearly independent solutions, which take on the following form. If you remember from differential equations, the way you solve something like this, you throw in a solution of the form e to the lambda t, calculate what the lambdas are, and that gives you your two independent solutions. And here's what it is, with C1 and C2 are undetermined constants. A couple observations to make. First, the value of beta of n. The value of beta of n better be positive. Why? If beta of n is negative, what happens? So if this is true, if beta of n is negative, then square root of the negative number is an imaginary number. E to the I something is nothing more than cosines and sines. Well, that's not a big deal, but, so this would be cosines and sines. Is there any way cosines and sines can ever satisfy that boundary condition? Cosines and sines never go to 0. As you go to infinity, they always oscillate between 1 and negative 1. So if we take a negative beta value, it does not satisfy this boundary condition. We rule them out. We are looking for specific solutions to this that satisfy this boundary condition. Beta of n being negative gives you oscillations, and they don't satisfy the boundary conditions, so we disregard them. So we know that beta of n is positive. Okay, that's good. Observations, still more coming. Now we're going to break this down into two pieces. Let's look at if x goes to infinity. So now beta of n is positive, so these are positive quantities. If x goes to infinity, what happens to these solutions? Well, if x goes to infinity, that blows up. Positive, positive, this is e to the infinity, which is infinity. So if x goes to infinity, you better not have that solution sitting around. This one goes to 0. That's okay. So when x goes to infinity, you only want one of these solutions. In other words, you want it to be that C1 is 0 in that case. Does that make sense? Because if C1 is 0, this is gone. The solution can still go to 0. If C1 is not 0, this blows up. So you want this to happen. This stuff that I'm working on right now is very important for the homework, and we'll have a lot of time to hash it out and think about it as we go along. But I'm trying to lay the groundwork here so that, you know, it won't be as confusing later. But does that make sense to everybody? If I have a C1 in there, I violate the boundaries. And the final one. What happens if x goes to negative infinity? Well, x goes to negative infinity, that's just fine. That goes to 0. That blows up. Can't have it. So, as x goes to negative infinity, your solution should look something like this. So we've made a grand total of 3 observations. One of them is beta event has to be positive. And the other 2 is that as x goes to infinity, we cannot have this contribution to the equation. And as x goes to negative infinity, we can't have this. Otherwise, we have solutions going to infinity. Now, what this psi of n represents is, for instance, in E and M theory, it represents the electric field. Obviously, if the electric field goes to infinity, it's bad news for who's ever at infinity. Okay? And we know that doesn't happen. Like, okay, I guide him out here, and by the way, there's an electric field that's, you know, blowing up a building over there. What we know is the field goes to 0 very quickly outside of this range. Okay, and it just does it by this. Now, this is easily mathematically to say this statement. What do you know about the computer, however? What you know about the computer is, if it's trying to calculate these things, it's going to only calculate that 0 to be 0 to 16 decimal places. That's not really 0, is it? Or you can think of it another way. In this system, you have numerical round-off going on. Numerical round-off is going to make its way to give a little bit of contribution over here to C1. Now, this might be tiny, 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 down on the order of 10 to the minus 16. But now, this, how big does this get? If beta n is around 100, then this is like 10. Square root of 100 is 10. 10 times x, well, if x is even fairly moderate, like 10, you have e to the 100 there. E to the 100 is a lot bigger than 10 to the minus 16. Catch my drift here? This, despite the fact you said, oh, this is 0, the computer doesn't know how to make a 0. It only knows how to make a 0 up to 16 decimal places. And that's enough room for this thing to go, oh, well, actually, you know, if you go far enough out in x, I can still get you. I can still blow up. So this is something we have to think about when we write a code. Because we cannot get around the fact that the computer doesn't know how to make a 0. Okay? Always keep that in mind. That these are things that seem obvious from an analytic point of view, like, yeah, just set it to 0, done. I don't have to worry about it. You do have to worry about it. And we will see this in your codes. Often when you write the program, you all of a sudden see this thing go shooting off on the, when you start to solve it, you get this thing blowing up, and you go, what's going on? That's what's going on right there. Okay. Now, here's the critical observation. That's one of those things that if you haven't taken up meditation, it's a good time. Often this next step that I'm going to make here is very confusing for people to think about for a bit. And I'm going to try to lay it out as clearly and concisely as possible. But then you have to think about it and think about what I said, and you got to sit there and like feng shui it in your brain somehow. You know, om, om, om. How do you say that in French, om? Is it the same thing?
Yeah, yeah.
Oh, yeah, yeah, om. Okay, it's universal. See? French say it that way. Yeah, om. Anyway, we do this to try to understand this next step. But it's a very critical, important observation for solving this problem. What we've done is we've taken a second-order differential equation. What you know about second-order differential equations is that it has 2 linearly independent solutions. Now, at the boundary, however, notice, for x going to infinity, we must be on one solution. In particular, at infinity, there is only one linearly independent solution. Right? Now, here's the step that you make. You say, well, if there's only one linearly independent solution for this, at infinity, essentially, it's acting like a first-order differential equation. Okay, you get that? At infinity, I only can have this one linearly independent solution. And so, essentially, the behavior out at infinity is acting like a first-order differential equation. That is the critical observation that you want to make. At negative infinity, same thing. I'm constrained to having one solution only because I cannot have this thing going to infinity. Again, at the boundary then, towards this negative infinity, my solution is acting as if there is one linearly independent solution out there, which means a first-order differential equation. So the connection I want to make here is the following. So let's look at x goes to infinity. I know that my solution has to be like this. There's essentially one linear independent solution out there. Well, if I only have one linear independent solution, again, it becomes then like a first-order differential equation. Well, what's the first-order differential equation which gives me that as a solution? Right here. Okay, that's the big step. Now, if everybody in their head were to plug this in here, you say, oh, yeah, that solves this. Right? Take the derivative of this thing with respect to x. Well, it just drops out on a negative square root beta n here in front. Well, and I have a plus square root beta in here. They drop out to 0. This is the first-order differential equation that has this as a solution. Okay? So essentially, the behavior at infinity is really being given by this differential equation right here. Okay? So again, important to wrap your head around that. And the reason we're going to do this is because this is how we're going to have to, this is how we're going to input our boundary conditions. Remember that the boundary condition states that this psi of n is going to 0. It's not 0. It's going to 0. How is it going to 0? You may ask. I know exactly how it's going to 0. We just did this thing here, which was exact. It's going to 0 exponentially. It's going along this decay. It's decaying exponentially. Very specifically like this. And at negative infinity, it's decaying exponentially like this. That's this specific shape. Well, to get that specific shape of decay, it's like imposing, it's like basically the behavior out there is given by this first-order differential equation. Okay, at negative infinity, we can do the same thing. At negative infinity, we can say, all right, my solution at negative infinity has to look like e to the square root beta of nx, which gives me the following behavior. Okay, so those are my two boundary conditions. In particular, remember that we no longer think, when we go to compute this thing, we are no longer thinking about x going to infinity, x going to minus infinity. We are now thinking about, we are in a finite domain, negative L to L. So really, if we think about it here, then here are my computational boundary conditions. At x equal L, which is essentially this here, what I have is d psi dn dx at L is equal to minus square root beta of n psi of n L. That's the boundary condition on the right. And the boundary condition on the left is d psi dn dx negative L is equal to positive beta of n psi of n negative L. Those are the boundary conditions. Okay? So notice, just like we did in the shooting method, what we're going to do is we're going to start off from the left boundary and shoot to the right. We're going to shoot from negative L over to L. Here's what I've got to shoot from. Negative L, try to hit this. Shooting from here, trying to hit this. These are my boundaries I'm trying to have satisfied. Okay? That's my launch. That's my landing. I have to satisfy both. I have to write an algorithm that does this. Okay. I have my boundaries. Now let's come back here. Erase this here. And let's talk about then setting up the problem for us to solve. The last piece of this is that everything we talked about in class on Monday and Wednesday basically set the problem up as a first-order system of differential equations. dy dt is equal to fty, where y was a vector. Now what we have here is a second-order differential equation. So anytime you have a higher-order differential equation, you've got to convert it into a system of first-order differential equations. That's just the way the ball game works. So the first thing we want to do is let's go and take our equation, which is given right by there. And this procedure you will always have to do when you encounter a new differential equation that's not first order. You say, okay, I have this differential equation. Let me write it in a way that I can then put it in the computer to do. So I'm going to make the following change of variables. I'm going to let the variable x1 be psi of n. And I'm going to let the variable x2 be psi of n, so d psi n dx. Now here's the observations to make. What is dx1 dx? Or I can just put primes now. Let me just do this. Take the derivative of this thing. What is that? Well, it's derivative. Just take the derivative of both sides. But what is d psi n dx? That's what x2 is. And in here, take the derivative of both sides. x2 prime is equal to, then that becomes psi n double prime. What's psi n double prime? Well, it's given right here. Psi n double prime is the minus of this. So that is equal to beta n minus n of x. Psi of n. What's psi of n, though? It's x1. So in total, what you have is x1 prime is equal to x2, x2 prime is equal to beta of n minus n of x, x1. Two first-order differential equations. Now, if I let the vector x be x1, x2, then what I find then is my differential equation is x prime is equal to 0, 1, this is what I'm solving. This is my system of first-order differential equations. This is equivalent to that. When I solve this, I get two components. X has x1 and x2. Once I get it, the first component, x1, that's just what I'm trying to solve for in the first place, psi of n. The second component of this thing, x2, is just the derivative of this thing. Okay? This is what I'm throwing into the computer. Specifically, all I care about is what's on this right-hand side. because the algorithms we're going to use, which are going to be able to built-in solvers, differential equation solvers that MATLAB has, that's all you have to throw in. What's the right-hand side? I'll solve it for you. There it is. That's the equation. What are the boundary conditions? Well, I wrote them over here like this. Let's take this one step further and say, okay, what are those boundary conditions then? Let me erase over here. The boundary conditions, let's take the first one there, says that d psi n dx at L is equal to negative square root beta n psi of n at L. Well, what's d psi n dx? That's x2. This becomes x2 at L is equal to minus square root beta n x1 at L. Remember, we have to make the transformation of the solution and the boundaries. And then the second one is d psi n dx at negative L is equal to square root beta of n, which gives you x2 at negative L is equal to square root beta n x1 at negative L. Now remember, I'm solving on some interval, negative L to L. So I'm going to launch from over here, and I'm going to try to hit something over here. In particular, I know that when I launch along at negative L, this is my condition. So what is my, if you want to think of it, what's my initial condition? My initial condition then is, well, right here. If you give me a value of x1, if I say x1 at negative L is A, then that's A, and x2 is square root beta A. Does that make sense? So my launch, say at negative L, it's my launch, sorry, is something like this, where I can pick A to be whatever. I can pick A to be 1, 2, 10, doesn't matter. All I have to do is satisfy this. So if I give you a value of x1, in other words, the actual launch height, x1, my x2 is just that launch height times square root beta n. That's it. That's your initial condition for that problem. And what are you trying to hit? What you're trying to hit is this here. What you're trying to land on is this fact here. You're trying to land on this relationship. You're trying to say, look, at the end, when I compute this thing out, all the way out, down over here, what I'm trying to land on is when I get here, what I calculate is x2 plus square root beta of n, x1, and that has to be 0. Okay? Now, what we're going to do in class on Monday, we're going to come back and revisit this issue, and we're going to consider a simplified version of what we've been doing here today. This is your homework right here, solving this. On Monday, we'll do a simpler version. Simpler a word? I think it is. A more simple version of this? No. Is simpler a word? Does anybody know? Or is it more simple? Simpler? We use it all the time. Okay. All right. Anyway, we'll do a simpler version, and we'll talk about how to do this. So you launch here, you try to land there, and the thing that we can change, the dial that allows us to change things here is not the value of A that we launch with, because this is a linear equation. Who cares about what A is? Because this A can just scale out of the problem very easily because it's linear. It's square root, it's the beta. What you're going to do to change what goes on here is you change the beta value. You change the value of beta until you get the right value of beta, that when you launch here, you land there. Okay? That's it for today. Have a nice weekend. I will see you guys on Monday.